All right. So, just with first principles, if I can just give a very brief explanation of where the formula comes from. Let's say we have some curve, so I'm just going to talk for a little bit and then we'll do the examples. Some curve which is f of x, all right? Now what we want to do is we want to find the instantaneous slope. So remember, average rate of change occurs over an interval, average slope over that interval. Instantaneous is occurring at an exact point. So the example I always give is the average speed camera safety zone versus a policeman with his speed gun capturing you at an instant. So occurring at an instant as opposed to an average duration. So what we're looking at is what's the instantaneous rate of change at a point. And one way we can do that is that we could go, all right, let's suppose on this curve, this has some x coordinate x, which means the y coordinate is going to be f of x. We put the x value into the function to obtain the y value. So we have some set of coordinates here. And then what we're doing is we're imagining another coordinate that is infinitely close to it. All right? So that it's like x plus 0.000001. All right? And so then the y value, the corresponding y value would be f of x plus 0.000, all those zeros to a 1, right? So we have the x value, and you put the x value into the function to obtain the y value. We would have those coordinates. The way we notate that is we go x plus h and f of x plus h. As h is approaching 0, we're saying h is getting really small. So what's going on there is if we have, this is coordinate x and f of x, this is coordinate x plus h that is so close to it that the distance between them is pretty much 0. So then we're doing, okay, well, what's the average rate of change between these 2 points? Average rate of change is just slope, right? F of x plus h, take f of x, divided by x plus h, take x. Okay, what does this simplify to? F of x plus h, take f of x on top of h. That's our first principles formula. Okay, so what we're doing, we've got some function here. We're envisioning any coordinate, and then we want to know what's the instantaneous rate of change at that coordinate. We have another point that's infinitely close to it, and so we derive the general formula for all slopes, first principles. Everyone remember that? Okay, average rate of change. Excellent. Now you'll find this funny. The background to it, like what I've just explained, that's not technically important. Okay, what you need to know how to do is to apply it, and so we'll get straight into that now. Now, is there an eraser? Got some tissues, as always do. All right. So, our first example. Consider the function x squared take 2x plus 4. Okay, find the average rate of change from x is 1 to x is 3. So if we sketch this, it's going to be some parabola, right? It's a quadratic. We know it's going to open upwards because it has a positive a value. And we want the average rate of change from when x is 1 to when x is 3. Okay, so we've got the x value is 1 and the x value is 3. We need the corresponding y values. So what I'm going to do is I'm going to put x is 1 into this equation, f of 1. That's going to tell me the y value when x is 1. We'll have 1, take away 2 plus 4, minus 1 plus 4, we have 3. When x is 1, the y value is 3. And then f of 3, we want to know the y value here, so we'll put 3 in. We'll have 3 squared, take 2 times 3 plus 4. 9 take 6 plus 4 plus 2, 7. Okay, so then the average rate of change, I like to call that the ARAC, the average rate of change, and that's just the slope of between those two coordinates, right? y2, take y1, divided by x2, take x1. So we'll have 4 on 2, we'll have 2. The average rate of change between x is 1 and x is 3 is 2. So the average rate of change. What that means is as x goes across 1, the average rate at which the function changes is that it goes up by 2. Up because it is positive. Okay, part B. Find the derivative function using first principles. Okay, so the first principles formula, that's what we're going to state first. Now, the first principles formula, we have first the statement about the limit as h approaches 0, and we need to write this step every time until we process the limit. The limit has h approaches 0 of 1 on h multiplied by f of x plus h, take away f of x. Now you can express the h underneath. I think this is the most effective way because then you're not dealing with 2 levels of fractions. We just have 1 level to manage for now. Okay, so all I've done there is state the formula, and now we're going to apply it. And to begin with, we will apply them slowly. All right, we will start slowly, and then we'll get to a stage where I sort of assume you guys know what we're talking about. So we've got x squared take 2x plus 4. That's our function, right? X squared take 2x plus 4. And so that's going to go there. We need f of x plus h. Now, we saw before, if we're finding f of 1, what we're doing is we're putting the number 1 everywhere there's an x, right? We put the number 1 there and we put the number 1 there. If we're finding f of x plus h, we're going to put x plus h everywhere there's an x. So we'll have x plus h squared. Okay, we're putting it there. Then 2 lots of x plus h, we're putting it there. And then this is just a constant that stays by itself. Okay, so all I'm doing is I'm writing the pieces out here that we're going to need for our formula, and we're ready to put it in. The process for first principles is always the same. So, step 1, plug what we have into the formula. So we're going to have the limit as h approaches 0 of 1 on h multiplied by first f of x plus h. That whole thing is going here. All right, I'm going to put it in brackets. So we have f of x plus h. Then take away f of x. I'm going to put that in brackets too. And we have our big bracket. So I'll just highlight the different components here. Here we have f of x plus h. Here we have f of x. And so we can see the resemblance from our original formula here. F of x plus h, done. Take away f of x. Okay, so really drawing it out. Anyone, any issues so far? Okay, so I'll just point out for you on page 2, all right? Process. It's always the same for first principles. Step 1, substitute it into the formula. Step 2, fully expand. Okay, we've got to fully expand. Always the numerator, never the denominator. Do not expand the denominator. So we're going to fully expand this numerator, which means right at the top here, we've got a perfect square. Now I'm assuming if we've done the holiday homework and we're at year 12, so we're pretty good at perfect squares now. Okay, a plus b squared goes to a squared plus 2ab plus b squared. All right, if you want any practice for that, let me know. Here we've just got distributive law, minus 2 expands into here, minus 2x, take 2h, and we have plus 4. All right, now I said it's absolutely imperative that we write this second part in brackets. And the reason that is because this negative must distribute to all of those terms, and it can change them. So we're going to have minus x squared plus 2x and take 4 when the negative distributes. So here we have fully expanded the first principles formula. Okay, so we're still on step 2. So input into the formula, expand, and now collect like terms. So we're looking along, we've got x squared and minus x squared. Those will cancel. We have minus 2x and positive 2x. Those will cancel. We have positive 4 and minus 4. Those will cancel. So now let's just restate what we have. We've got 2xh plus h squared take 2h. Now this is a checkpoint. When you're at step 3, this is a place where you can check if you're on the right track. You are on the right track if every term in here has a h, okay? If you have something in here that doesn't have a h in it, then you've made a mistake and you need to go back and check your expansion and collection of like terms. At this step, in all first principles problems, every term, that's something separated by a plus or a minus, every term has a h present in it as a factor, because now we pull h out the front as a factor. So we're going to pull h out the front and cancel it. Okay, so we've pulled one h off there, one off there, and one off there. If we were to distribute it, we would have the same as what we had above. The h out the front here cancels, and now we're ready to apply the limit. When we apply the limit, okay, so the limit, we're pretty much, the best way to think of it is we're substituting h is 0 in, and we're left with 2x take 2. So I should have equal signs down here. Okay. So what we have here is f dash of x, isn't it? We've got from first principles, f dash of x is the limit as h approaches 0. So we've found f dash of x. So I'm going to rub out my f of x plus h there now and just make a link. This is something that we'll keep stressing. 2x take 2, sorry. Now we sometimes use this language. So I'll just draw your attention to the table on page 12 as well. Okay, so our first function, we call this the function. We sometimes use y, we sometimes use f of x. You're expected to use both, all right? Now, this is our function, and we saw before, if you put any x value into this function, you can put 1 in, you can put 3 in, and it tells you the corresponding y value. That's the value of y given this value of x. The y value is equal to some function of x. All right, that's the y value. Next, we have dy on dx, the rate of change of y with regards to the rate of change of x, or f dash of x. This is the slope function, the gradient function. Now, if you put an x value into this function, it tells you the slope for any value of x. Okay, so that's expressed clearly in that table there. We're going to keep hitting that table over the next few questions. Okay, so part C says, find the instantaneous rate of change at x is 2. When x is 2, what is the instantaneous rate of change? So that was our part B. Here we're on to part C. If we want the instantaneous rate of change, that means we want the slope at x is 2. We're going to find f dash of 2. So this means I'm putting x is 2 into our derivative function. Explain the difference between part A and part C. Now, although these have the same numerical value, so for part A, our answer was the ARUC, the average rate of change. That was 2. And for part C, our instantaneous rate of change is 2. They have the same numerical value, but let's state the physical significance of the difference between them. So, average rate of change, so this is our answer to part D. Average rate of change occurs over an interval. Instantaneous rate of change occurs at a point. All right, so in other words, we found the average rate of change between 1 and 3. Between those points, the average, on average, over that interval, the change is 2, even though between them, it will vary. Okay, it will vary between them. You driving down the highway, your speed varies as you go up a hill and down a hill. Okay, even if you've got cruise control on, there's still minor variations. But your average rate of change will vary. Whereas at one point in time, you have a particular speed. So instantaneous rate of change occurs at a point. At one point in time, you have a particular speed. The average occurs over an interval. All right, so that's our answer to part D. Part E, find f of 4 and f dash of 4. Okay, f of 4. So I'm putting the number 4 into our original function. We're going to have 4 squared, take away 2 times 4 plus 4. So we've got 16, take 8 is 8, plus 4 is 12. F of 4 is 12. Find f dash of 4. So now we're going to put the number 4 into our derivative function, our slope function, our gradient function, okay? I'm going to keep using all of the different words that we use for it so that we get the hang of the notation. F dash of 4 is 6. Now, there are 2 different numerical values here. We're required to explain the difference between them. And yes, this is a very common test question because we just really want to draw out, do you know the difference between what each function does? Refer to our table. When x is 4, the y value is 12. When x is 4, the slope is 6. So, how can we articulate that? When x is 4, the y value is 12, and the slope, the instantaneous rate of change, the slope is 6. Very good. Okay, let's just do some first principles mashing now, then. Any questions about any of that one? No? So that's a good recap of Year 11. This next one will be a Year 11 question as well, but we'll still go through this one together, and then I'll get you guys to have a crack at one. So this is question 2A. Find the derivative of the following functions using first principles. So the function that we have here is 5x take 2x squared. So for first principles, all right, still I'm going to break it down to its parts. And if it helps, I encourage you to do that. We should get to a stage where it's not necessary, but we've got f of x, we need f of x plus h. So all that's going to be is this one, okay? We're just putting x plus h everywhere there's an x. Okay, let's follow the process. Step 1, write the formula. Don't forget your limit. Substitute in. Now I'm going to keep writing the formula. You don't need to write the formula. I'm going to keep writing it for the sake of pointing up here where we're substituting things. Okay, f of x plus h. Take away f of x. There's some space. All right, make sure we've got brackets on the second one. Okay, someone will do it today. Don't be that person. So that the negative can distribute. Okay, so step 1, we put it all into the formula. Step 2, fully expand and collect our like terms. Now, if you know what's going on, feel free to run ahead, but I'll keep working my way up here. So we'll distribute the 5. We're going to have 5x plus 5h. Now, this expansion here, can I just stress, I see too often people try to rush an expansion and they get it wrong. It's better to do things slowly and properly rather than get 6 steps down here and go, hang on, something's wrong, rub it all out. Do it slowly but properly the first time. So for that reason, I'm going to leave the 2 there and do the perfect square expansion and then distribute the 2. All right? Not only because you're multiplying by 2, but also because you're distributing a negative in it. Okay, so that's going to be my advice. If you have multiple expansions to do, and we should know BEDMAS, right? Exponent, brackets, exponents, and then the multiplication. This negative here is going to distribute. So my expansion is occurring over 2 steps, just to make sure I do it properly. We'll have 5x and minus 5x will cancel. We'll have minus 2x squared and plus 2x squared will cancel. Let's restate what we've got. Take 4x each. Factorise our h. And apply the limit. Okay, very good. So I'll pause there.